Okay, so I'd like to give you a couple of examples of some position time graphs, velocity time graphs, and motion maps to kind of walk you through how you can sequence from one to the next and how one can be interpreted to lead you to what the next graph and or motion map would look like. So first, we'll just start with a position time graph here, and we'll go with the standard constant velocity that we've seen before, just like our tumble buggies in class. And I'll remind you that what we've been saying is that the velocity, what we found, is the change in position over the change in time, or delta x over delta t. So, since that's the case, what we see here is this line here is a straight line of constant slope, which again is the velocity. Slope of a position time graph is velocity. That's a constant velocity that's positive. So a constant positive velocity is what we see in this motion. So what does that look like on a VT graph? Well, this area is positive velocity. This would be zero velocity along the t-axis. And this would be minus velocities, or negative velocities. So this, again, constant and positive slope means constant and positive velocity. So our line then would look like that, because we're saying that it has a positive value and that value remains constant throughout time. So constant positive velocity, meaning the ratio of the change in position over the change in time is constant. For every second in time, we have the same change in position every second. So every time we go over 1 second, we have the same position change for that second. And so then the motion map. Once we indicate where the zero position is and where the positive direction is, we see that on the position time graph, it starts, well, since I've drawn it here, apparently it looks just above the zero position. And so maybe we'll say, and I say above, what I mean is on the positive side of zero. So that means on my motion map, my first dot I would maybe put on the positive side of zero, I suppose, to be the most accurate. And because this is a constant velocity, as we see here, which is indicated on the VT graph as a constant velocity, then the motion map would all have constant length arrows for our velocity, indicating to us that this object is traveling at a constant velocity every moment in time, having equal velocity. Okay, so the motion we had for the next setup here was for the go car that we had that would roll down the ramp. And so that is going to look like what we did in class with our data that gave us this up curve. And we had to then figure out, this is for a position time, this is for a velocity time, and again we will have a motion map here. So we saw then that in this case we don't have a constant slope. So our velocity is no longer constant. We don't have the same ratio of rise over run, of position change and time change. So because that's not a constant ratio anymore, we have a velocity that's getting larger. We found out that on this graph, how you see a velocity getting bigger as time goes on instead of it looking like this, now we see it looks like this, showing again that the velocity value is getting larger as the time goes on. So, increase of a velocity over time, because the slope of this graph has been increasing. Again, if I were to draw some tangents to the curve, the steepness there, let's see if I can move that a little bit. So the steepness at that point, which looks to be maybe around here. Well, I guess I didn't put that in the right place either. I guess we'll move the whole thing. So that would be a tangent at that point, and now a tangent at this point, perhaps like this. So that's telling us how steep this curve is, maybe at that point. So clearly, as I said before, this curve has an increasing slope. It's not as steep here as it is later in time, meaning these velocity values have to be getting bigger as time goes on, because our slope here is getting steeper. Now we found out that this graph, the velocity time graph, the slope, or the rise, which is the change in velocity, over the run, which is the time, or the change in time, is what we called acceleration. So we had acceleration then as our slope of a VT graph, or a velocity time graph. Now, with an increasing velocity, how does that translate to the motion map? Well, again, if we look at the position time graph, I start very near the zero position. So I will do that as well on my motion map, start very near the zero position. And we start with a very slow velocity, because the slope at the start is very shallow here, not very steep at all. So my first arrow will be rather short. And then as time goes on, as this slope continues to increase, and as these velocity values continue to rise on the VT graph, my motion map is going to get to where I have longer and longer arrows indicating, again, that my velocity is increasing. Every second, my velocity is getting larger and larger, as shown by the larger arrows. And again, the last question we have to answer is, what direction is my acceleration? Well, in this case, my acceleration is based on the slope of this graph, because a rise of change in velocity over a run of change in time, this is acceleration, and this is the slope of this graph, which is positive in this case. So we have a positive slope, therefore my acceleration is in the positive direction. Now notice, my velocity is in the positive direction, my acceleration is in the positive direction, and I am speeding up, getting faster every second. So when the velocity arrows and the acceleration arrow point in the same direction, we have speeding up. Now if we go back over to this other graph here, we didn't draw an acceleration on this graph. And so what would the acceleration be on this graph? Positive, negative, or zero? Well, we look at our VT graph here, and we see that this slope is a zero value. We have no rise over run. Therefore, we can say then that the acceleration is zero, because as you see, our velocity is not changing. We have the same value all throughout time, therefore our acceleration equals zero. Okay, now I'd like to do one more example. So I'm going to see if I can get rid of some of this stuff here. Let's see. This is taking a little longer than I had hoped. So I'd like to take a look at a position time graph that looks like this. What if the position time graph has a curve like this? So the question then becomes, what would a velocity time graph look like for that kind of motion? Well, again, the question we have to answer is, what is the slope of this graph? Well, it's not constant. So we do not have a constant velocity here. There will be a changing velocity. So how is it changing? Well, I'm going to draw a few tangents to the curve on this curve here. So it looks like at the start we have a tangent that looks about like this. Let's see if I can grab that and move it. Or I'll move that. So that looks pretty level to me, which looks like zero slope. Now if I go down further, like maybe in this area of the curve, I'll draw another tangent. Wrong color. And let's see if I can move this thing around. Right there. Alright, so again, this tangent is about in this place. This tangent is about in this place. And maybe I'll draw one more tangent that's maybe down in this area here. So another tangent to the curve. Like that. Now, what are we seeing here? And that looks like that might be a tangent at about this location. So what is this telling us? Well, if you look at the slopes of the tangents to the curve, that's a zero slope. This is a negative slope. This is an even steeper negative slope. So what is that telling us? That apparently, look at this curve, as it curves down like this, the slope is going from zero value to negative to very negative. So what does that do then to how we draw the velocity time graph? Well, the slope is going to have to start at zero, or I should say the velocity, which again is the slope of the position time graph. So that slope starts at zero, so that means our velocity is going to start at a zero value, at time zero. Now, at some time later, we have a negative value for slope, which means we have a negative value for velocity, which is in this region of the graph. So again, if it's at zero value near the beginning, and it's a negative value sometime later, so maybe in this area, a negative value for the velocity. Now if we look again at the graph, another few moments later, we have an even steeper negative slope, meaning, again, it's even a larger value, but it's negative, which means it's probably going to be even further down on the velocity axis at a later time. So we can make another dot that might represent that third tangent to the curve. And so what do we see? We see that our velocity values are getting larger but more negative. Again, larger again, but more negative, further away from the zero value of the velocity. And so we could connect those, and we see we have a straight line graph But now we have a negative slope here because the velocities are getting more negative, because the slope of this graph, of the xt graph, is getting more negative. And then so how does this translate to a motion map? Well, we mark our zero position in our positive direction, and it looks in this case, if you look at this position time graph, the object starts at time zero with a positive position. So we might draw our initial dot for our object at a positive position far away from the zero on our motion map. Now what kind of arrows will we have? Well, at first we had nearly a zero slope, and it just starts to incline in the negative direction. So that means our arrows are going to be in the negative direction, and they won't be very long at the start, but they will get longer as we go because these slopes are getting steeper, and steeper slopes mean faster, and faster means longer arrows. So again, we'll draw even longer arrows as the object continues to approach the zero position again, which is on the t-axis. And again, these arrows are slowly approaching the zero position. And again, the last question would be, what is the acceleration of this object? What direction is it? This is a negative slope. So a negative slope here means we have a negative acceleration. And again, if we look at our motion map, we see that the velocity arrows are in the negative direction, and the acceleration arrow is in the negative direction. Therefore, the object is speeding up. Just like we had on this one, the velocity arrows were in the positive direction, acceleration in the positive direction, the object is then speeding up. So there you have it. I hope this helped.